Hello, my name is Marek, and today I will do a little bit of a recap of double bracket quantum algorithms. It will be meant to be an introduction to the methods we use on the mathematical side and to highlight the elementary parts of it. Let me share the slides. The slides will be available online. All right. So you can use this QR codes or go to slides.com. My name is user. And yeah, it will be today a personal story of what was going on for me in the last 4 years. I arrived to Singapore in October 21. Then about half a year later, I posted the proposal for double bracket quantum algorithms on the archive. And the talk summarizes a bit what I learned. It hopefully simplifies things, which to me is a sign that I learned something along the way. Before I arrived to Singapore, I never worked on quantum algorithms previously. Now we have 9 papers on the archive. This includes actually 2 experimental explorations. And the cool thing is that 25 people contributed to this effort along the way. So it was really a beautiful walk through the mountains as I used to know it, but intellectually so. It is actually worth mentioning that this has been a research program. Previously, I was always jumping between ideas as we do. And here we really developed a line of research. And what was guiding us were the mathematical observations. And there was really a wealth of things that we're waiting to discover about the analytics behind all those structures. And I will tell you today how Riemannian geometry is key for all that, and you will see it as the unifying feature. So I will tell you about double bracket quantum algorithms. I will start with some comments about quantum algorithms and quantum computing. Then I will talk about Riemannian geometry of the unitary group that will be kept at a more elementary level. Then we will move on to using this for quantum algorithm design. But before that, as kind of a habit for critical thinking, I will make an interlude to organize our thoughts about how to use this theory of Riemannian optimization in quantum computing. What would be the good tasks? I think that's quite a timely thing to consider in general. All right, so moving on to the first part. For me, a quantum computer is a system that involves inside of it a quantum system, for example, ionized atoms, loops of or superconductors. That means that we can actually make it. So we have explorations with in-house fabrications in Rainer Dunke's lab, for example, here in Singapore. But also around the world, you will see people setting up relatively simple elements and then being able to make some mini prototypes of quantum computers by playing with quantum systems. What it also means is that some people kind of are excited about this, what's going on in the stock market, but it also shows how it was possible for some more entrepreneurial researchers to go on and start publicly traded companies. We will need to see where this effort will go. Well, a quantum computer is a quantum system that will be modeled by a finite dimensional vector space. What it means for us is we take n qubits, then the vector space that we will consider will be exponentially large, but it's just a linear algebraic structure, which I find is often worthwhile to think about. The quantum computer will need to be modular, so we need to be able to add more of its components to make the dimension of the vector space D. We need to make it grow. This means we will take more qubits. Once we have more qubits, we need to be able to make them programmable. And what it means is that there will be some physical operations that change the quantum states of the qubits. Those quantum states are vectors in this finite dimensional vector space, but those operations must be reproducible and reversible. In the end, if you look across the spectrum of ideas, the programmable operation will always be some electromagnetic radiation that we apply to the components. To make it reproducible, we will use fast electronics, and to make it reversible, that's the physics challenge, basically to keep it cold and nicely shielded. And finally, when we have the operations, we need the notion of universality. So if we repeat those programmable operations in all possible ways, we should be able to find any vector from that finite dimensional vector space that we have. And what it means in practice is that we are using results that were derived by physicists in the 90s. The discussion in Nielsen Schwank from 20 years ago is still valid, in my opinion, and that's my recommendation for the go-to text as the basic go-to. Okay, so what we have is that for good or for worse, quantum computing is influenced by physics. And just as a remark, the Nobel Prize this year is not for quantum computing, it's for the fundamental discovery that when you take loops of superconductors, you will have this quantization that I talk about in the second row with the finite dimensional vector spaces. So the three professors who got the Nobel Prize could still get another one if quantum computing delivers on its promises. But for now, it's all about physics in the spotlight, about the possibility to create those systems. So that's a very cool story. And okay, let's just recap how their discovery has led to the effort to build quantum computers experimentally. Our idea of a quantum computer could be the following. We need to have an experimental setup, which includes inside of it a quantum system B, and that setup A allows to manipulate the quantum state of the quantum system B. This is modeled by multiplying unitary matrices to vectors from a finite dimensional space. Okay, so this second sentence is the key mathematical part of what we want to be discussing. So as in the picture, we have a system A, a basket, it contains fruits inside, and the challenge is to keep a naughty cat away from destroying our valuable things we want to operate on. And for quantum computing, we have a similar situation. The whole apparatus will be the quantum computer, and the qubits in this picture will be only inside of this glorious chandelier. Actually, this monumental structure is only the inside supporting the dilution refrigeration, which helps shield the qubits from noise. So the naughty cat in the illustration above here is just the noise, the thermal effects from all around. If we can get it done, then we can use abstract models of quantum computations. And let me describe kind of maybe a general way of thinking about quantum algorithms next. So I will need bracket notation throughout the talk. So if I have one qubit, then the vector space will be two-dimensional. It will be a complex vector space, but it's basically spanned by two orthogonal vectors. We will denote them by the so-called cats. So those are just two orthogonal vectors that will span for us the two-dimensional vector space. Once we take a linear combination of the vectors, it has the physical meaning of a quantum superposition, hence my background of the slide. And this quantum superposition is essential. And we use this notation because later for computation, it's useful. In physics, we use often Greek letters for denoting the vectors. It may seem strange, but it's very useful for us in the end. So what Dirac proposed is that if we have a dual vector, so the Hermitian conjugate of the vector in the vector space, we just denote it as the flipped cat. And then instead of taking scalar products, we can just adjoin them together. If we have a matrix acting on the vector, then we will just write H times a cat. If we want to take a least square scalar product, that's an expectation value, statistically speaking. And then we would just write the sandwich bra H cat. Okay. So this notation here will be important. The meaning of it is really nothing else than we would have in regular linear algebra. I will be moving forward to look. We will look at this as a cost function later on in the talk. All right, so what is a universal quantum computer? It's a physical device that operates in nature and prepares for us all possible vectors from this finite dimensional vector space. So it's a machine for realizing linear combinations in nature out there in the lab. And as you see, even for 4 qubits, expressing everything by hand will be difficult. And the way we keep track of it and make everything algorithmic is by studying unitary rotations applied to a reference state 0, 0 that give us this precious state that we want, okay? And then we will be approximating those unitary rotations by certain decompositions, which we call quantum circuits. So to set it up, let me define unitary operations. This will be important in terms of geometry because we consider just d-dimensional arrays of complex numbers. Those are matrices. And we consider a special subset of those matrices such that the inverse of the matrix exists and it's easy to compute. You just flip the matrix and take the complex conjugation of every entry. That's the Hermitian conjugate. So if the inverse of the matrix is such Hermitian conjugation, it's a unitary matrix. And they are very similar to rotating spheres. I will be showing the watermelon every time I talk about rotations. Now, it's actually worthwhile to spend a minute to discuss that the set that I just described here, the set of unitary matrices forms a group. The group will be multiplicative, so I can multiply the two matrices together and check whether the Hermitian conjugate denoted by the dagger is the inversion again. So we can use just the standard rules of flipping m prime with m here, combine them together by where unitary matrices, so this is identity, and then the second bit is identity again. So we find that the multiplied matrix is unitary again. That's important because if a quantum computer operates in steps, it will do a sequence of mapping psi into psi prime and then psi prime into psi double prime. So if I join those two operations together, clearly it should be a physical operation. And this group law here is this compositional law that we want. The algorithms that I will describe will be very much within the mathematics of this group law. We will be composing things together, and that will have the meaning of sufficiently well composing things together and finding hopefully a useful state at the outcome within the space of operations that we can do. Okay, so now I'm coming to the last row of the discussion that I did for the introduction. Let me just define the notion of universality. It means that we will have a set of basic unitary matrices. So I select a bunch of unitary matrices, and I want to see that I can approximate any other larger unitary matrix, larger in the sense that it needs some decompositions. So let's say I can fix a set of K matrices for the group of dimension D, such that if I choose any unitary matrix here, then there will be some sequence such that I can approximate the input matrix here that I selected by some kind of sequence from this gate set. Okay, so what it means is that the set of unitary matrices is a little bit like a sphere for a qubit, so dimension d equals to it is. And then when we have 2 points on this sphere here, we can compose them together, obtaining a new one. And then we can keep composing them in a special way. And at some point, we cover the whole watermelon, the set of operations that we have. Now, the thing that I want to define next is that unitary synthesis. So you give me M, and I need to find the sequence. It's quite a hard optimization task. We refer to it as unitary synthesis. So find for me a decomposition in terms of the gates. Of course, it's one thing to show that it exists. That's the notion of universality. Unitary synthesis is using that existence to actually constructively find it. Okay. Now, double bracket quantum algorithms are a framework for this, so we will see it later again. All right, so I described part number 1 about the setting of the stage for the unitary group. I hope that was clearly motivating that we should look at it. And the next thing that we want to do is to look at the Riemannian geometry of it. If you are not familiar with it, then I will actually define the essential features of it. And now first I kind of conceptually talk about it. So the watermelon will be kind of visualizing this geometry for us. We will need to look at the generalization of the sphere. For 1 qubit, the sphere is a great model of those unitary quantum operations. If we want to go beyond that, then some parallels will remain. So the set is compact. So here, my friend was able to wrap the watermelon in his hand. That's not always possible for mathematical structures. So that remains. But for example, very easily we can lose convexity. So that's why I like the watermelon, not just a regular sphere, because you can imagine that this has some crests and values if the color coding would be not a smooth surface, but actually color coding the depth. All right, so some things will stay, some things will go. And the most important things that we want to keep in place is that if you imagine I take this watermelon and pop it on the table behind it, then that table will be tangential to the watermelon. So if I rotate it, if I take some directions, then this table will still stay tangential even after the update when rotating the whole set. Okay, so the tangential direction is important. It also tells us the notion of a straight line. So I take a direction, and even if I think that I'm going straight along of the equator, I will be actually wrapped around through the intrinsic underlying curvature of my space. So let's see a little bit more about this. This curvature will be very important for what we want to discuss. So the unitary group, I state just the fact, is a Riemannian manifold. It is an embedded manifold, so it comes as kind of a projection from the embedding set of matrices. That's why I was discussing it in detail before. And now the tangent space, I'm only defining it, but the definition is simple. For unitaries, the Hermitian conjugate is the inverse. For the tangent space, those will be again matrices of the same dimension. The Hermitian conjugate flips the matrix. So we have anti-Hermitian matrices. It's the same as taking a regular Hamiltonian matrix, so a Hermitian matrix, and adding an I here. Okay, so that's the notion of the tangent space for us. I will be using W and H interchangeably. And then given those tangent space elements, those vectors give us directions. And then I can go on the straight line in that direction. And that's just the matrix exponential defined by the exponential series on that direction, where S is kind of telling us how far do I go along of that quotation mark straight line. Okay, so those are the geodesic of our Riemannian manifold, the unitary group. Okay, the matrix exponentials. Physically, this is nothing but fixing a single Hamiltonian and waiting for some time duration as this Hamiltonian is acting. The problem is that computing a gradient must output an element of the tangent space. I cannot update my state through an operation which is not unitary. And so if I take the gradient, just taking some partial derivatives over the entries over my coordinates, if those coordinates come from the embedding manifold, then very quickly the gradient, the partial derivatives, will point away from the tangent space. So I need to have a way to project it back. Okay. And this projection we can construct. I will actually explicitly derive it for us. But we need this new notion that is kind of a tangential gradient if I have some cost function. Okay. The next thing that I want to discuss before I come to those tangential directions is that the unitary group is a manifold which is curved. If I have a flat space, so the flat space behind the watermelon, I can go on a rectangle. So I can go down, I can go left, I can invert what I did by going down by going up, and then I can go right again. I will come to the same point. Now, on the unitary group, this doesn't happen. So for a qubit, the two-dimensional sphere is a model, and you see if you're close to the equator, if I start by going south, then I can go west. I can undo going south by going north. But as you see in the picture, if I undo my step to the west by going to the east, I will spiral away from the point of origin. Okay, so where I land is obtained by composing together the operations I did. I went south, I went west, I went north, and I wanted to undo going west by going east. And that is in general not the identity. And so the manifold is curved because I don't come to the point of origin. This is how we constructively use the notion of universality. And what is important to keep in mind for later is that unlike in flat space, these four steps spiral away from the point of origin. We will next study what is this operation. We said it's a compositional group. So composing those four operations together will be inside of the group again. But now we need to ask, what is it if it's not the identity? Okay, it's a very fundamental fourth cycle. It tells us about the curvature. And answering this question is the key point for algorithms. So to prepare the stage for answering this question, let us consider a new unitary. We are working with a quantum computer. Maybe we should consider some exotic unitaries. So let's do that. Let me take two Hermitian matrices and then take the commutator of those two matrices and take the matrix exponential. My claim is that this is a unitary matrix, and this is something I want to show you. So we will want to show that this exponential is unitary, and we will take a few steps. And the key thing that we want to show is that what I'm exponentiating here is an element of the tangent space, so it's an anti-Hermitian thing. So we can do this by an explicit calculation. The commutator is defined AB minus BA. I take the Hermitian conjugate. I need to flip B and AB, and apply the Hermitian conjugate. But they are Hermitian, so without writing it out, I see that this is minus the commutator. So that means that this is an element of the tangent space of the unitary group, and so I can exponentiate it to get a geodesic. Okay, so that's a unitary matrix. We can check that this works. So if I take my matrix defined as the exponential, take the Hermitian conjugate, then it's the same as taking the Hermitian conjugate of the exponent. I get minus, and then if I would multiply this and this together, the exponents commute together, and that means I get the inverse here by multiplying things together. Okay, so we can really double check our calculation once we have this. Okay, so once I show this, I directly see that this is the unitary, but we can check it by hand. Okay. So usually you don't see those commutators, but I would advocate we should be seeing them everywhere now, wherever we look. And the way to see them is to say, well, actually, this exponential of the commutator gives me the answer. If I'm spiraling away from my point of origin in the fourth cycle, where do I go? This is the answer in first order. So if you make this fourth cycle very, very small, the error away from this will be vanishingly small. And you see that this is telling you where you go. Okay, this is actually quite a beautiful answer. We make this fundamental fourth cycle, and on a unitary manifold, we have something called the Lie bracket, which is the commutator. So I have two elements of the tangent space, the Hermitian matrices. I take the Lie bracket of those, I get a new element of the tangent space, and that gives me the answer if I compose them like this. This is called the group commutator. I'm switching the background because this is the main tool of double bracket quantum algorithms. And that was my contribution early on to take this composition seriously and then see what kind of commutators I can implement by already knowing which things are expressed through commutators. So my quantum algorithms use such unitary matrices, and the cool thing is they are implementing Riemannian gradient descent. Let me tell you now next what I think Riemannian gradient descent can be useful for in quantum computation. So next I want to go to this interlude to say, what can we use those algorithms for? And in general, what are the good tasks for quantum computers? And I think it's intimately linked with using Riemannian gradient descent as an optimization method. Okay, so to my mind, there are four stages of developing quantum algorithms. The first one is actually to do nothing and think, because we first need to find a good challenge such that our old school quantum computers cannot solve the problem efficiently, and it should be a useful problem. Okay. Then once we have it, we need to make a design change. I will have some input of my computation, and I need to be able to encode my task that I'm trying to solve for my industry partner or the client of the quantum computer. Okay, so there needs to be some encoding of the problem, and that's a design choice how we will do it. That will then determine what we need to do. And what we need to do is phrase the mapping of the trivial input to the non-trivial output that we want to compute, and we need to phrase it through a sequence of unitary transformations. We will be composing them. The watermelon will be keeping track of our rotations. It's a group, but we need to find those operations. And that's this difficult task of constructively finding those decompositions that I defined before, unitary synthesis. And finally, once we have unitary synthesis, usually we will do it in terms of operations that we know how to decompose into the programmable operations, those hardware operations. So we compile down to the physical gates. Double bracket quantum algorithms are a systematic framework for unitary synthesis, and I will show you how this arises from geometrical considerations. Before we go there, let's, like as a habit, let's think about how to use quantum computers meaningfully. That's an important thing that is very relevant to all kinds of startups and companies in the field right now. So quantum computing cannot be useful if the problem that can be solved quickly on a classical computer. Obviously, we already have those machines. We can continue using them. It will also not be useful if solving the problem isn't important. And a quantum computer cannot solve problems that are too hard. Okay, there are also limits on its computational power. So it gives you examples. For example, recently there were claims that trade bonding on the stock market can be done faster by using a quantum algorithm, and then people looked at it more in detail. It's a big claim, so people scrutinize it, and they said, well, maybe I can actually have a better classical strategy. And the system size is not so big, so I could still simulate it on my old computer. So then the other thing is, okay, maybe we can come up with a problem that is very hard for classical computers, but actually is not otherwise useful. It's useful only for showing that a classical computer cannot do it. So that's not particularly relevant in the long run. And there will be problems in industry like mixed integer programming, shortest vector problem that we don't think the quantum computer will be able to solve efficiently. My claim is that material science is a type of a problem we should take up, okay? But there are many people who claim many things in quantum computing. How can you verify it? The problem is when a lot of people can gain by having something to say, some of us will not resist the temptation to speak without having much to tell, and this creates hype. So how to probe me whether I'm hyping something worth doing? Well, we need to ask critical questions. So what happened with hype is that when Short showed in the 90s that quantum computers can break cryptography, it created a rabbit hole of exploring this new uncharted jungle of possibilities. 10 years later, he beautifully lamented, why have not more algorithms been found? Okay. His answer was either because the easy algorithms can be done on a classical computer, or we have no good language for finding those algorithms. If we zoom forward to today, you have this website that you can click from the slides. If you open them, Quantum Algorithm Zoo, and there's a zoo of applications, but there are not so many distinct algorithms. My answer why most of algorithms are applications of underlying solvers is that I can think also classically. Classically, we can reduce sophisticated procedures into a series of decision problems. So such a reduction can be done. And quantumly, what is a decision problem? Well, it's asking, can I find a state psi such that the expectation value, the energy of some Hamiltonian cost function encoding my decision problem, is that number lower than a threshold, okay? And we know that probably the only speed up we can get is the Grover speed up, which is quadratic. So there's some limitation on what we can do here as well. Okay, so I'm saying material science is a useful thing. There's this whole difficulty of finding good speed up, and then there's the hype. So why is it not hype? Well, I can answer probing questions. So why material science? Well, imagine we can do material science with the algorithms that we are building. And then imagine you create a photovoltaic cell, which from the beginning is already 1% better. You get a better competitive edge, it will be useful, and then you can run your algorithms. What do we need to do for that? We need to find states that are low energy states of the Hamiltonian describing the material. And then we need to study the physics of it using the quantum computer. Okay. It's maybe still research and design. There are risks taking up such research, but it's very solid, and we can look at that if we have the machine for us. And how to do that is quantum circuit synthesis, developing the algorithms of the type I described. And the nice thing is that if we can do it, material science asks questions in terms of natural Hamiltonians. So hopefully we can study that. Okay. If you're not buying those answers, the other answer is that if you look at researchers from companies like Google, they actually talk about Google making revenue out of studying materials with utility scale quantum computers. So I'm not the only one hoping that we can have a contribution there with the work that we are developing in theory today. Okay. So we need to optimize among all operations of the quantum computer to get a low energy state, minimizing this energy cost function. My claim is this is what we need to do. And the other thing that I will tell you is that Riemannian geometry can lead to such quantum algorithms that develop such things. Okay. So we are going now to look at that. part number 4 is to ask how those group commutator formulas can be used for optimization of the cost function. Okay, so we have a cost function. It's the expectation value of the Hermitian matrix H. And now what we want to do is we want to take an element of the tangent space, apply it to the state, and hopefully lower the cost function. Just as a warning, not every choice of the tangent space element A will be useful. If I choose it to be the one that I have with the cost function, it's already a Hermitian matrix, so why not try it? Well, that one will not change the energy, as we know from simple calculations using commuting matrices. So we need to find directions in the tangent space that are more useful. So either this will be the Hermitian matrix A, where I need to adjoin the imaginary unit, or it will be the anti-Hermitian matrix W, but they should be pointing towards a direction that decreases the energy. So there is a unified way of finding such directions. The way to go about it is the Riemannian gradient. The Riemannian gradient is defined as a vector in the tangent space, and it is a unique vector such that all directional derivatives of the cost function are a projection onto G. Okay, so I explain this sentence now. If I have my Riemannian gradient G and the cost function f, I can consider the directional derivative, which means I take some direction w and I ask how is my cost function changing in that direction. So I have my point where I'm working, my x, and then I modify it in the direction of w, and then I scale it down towards 0. So that's a notion of a derivative, and it's called the directional derivative because anywhere we look in the tangent space, we will have a different value of that number. The Riemannian gradient is a simple way of computing using the scalar product in the tangent space. The tangent space is a linear vector space. We have a projection operation there. And you see that this complicated thing, we studied it in analysis and it's going through a limit. This set of numbers here on the left is given by a projection. That's the beauty, the power of Riemannian geometry in a nutshell. I'm not proving this. It's a characterization that mathematicians have proven comparing to other possible definitions of the gradient. The nice thing is that this is an element of the tangent space, so it directly implements for us this projection from the embedding manifold that we need. So our cost function f will be the energy, and now I will show you what is the matrix G. I will take two elements of the tangent space. The projection onto the state where I'm working, the equivalent of the point x of the manifold, is already Hermitian, and the cost function comes with a Hermitian matrix. None of those matrices on their own decreases the energy, but we will use them. And then the next thing is to ask how to take projections in the tangent space. Our notion of projection will be the Hermitian, the Hilbert-Schmidt scalar product. So we take the Hermitian conjugate of the input G, then multiply it by W, take the trace. That's our notion of the scalar product. Okay. And then if we want to prove what is the form of G, we are working here with trace. And just as a reminder, this elementary property of cyclically shifting C to the left will be essential. Okay, so those three ingredients I can use and find the form of G for you. So the cost function is E. We update it in a direction A. I need to take this derivative in S for how my cost function changes if I'm rotating in the direction of A. And this means I just need to take the derivative in S and evaluate it at 0. By the Heisenberg equation, we see that this will be just the commutator that will be left behind, and I can rewrite the expectation value through the trace. Okay. So this number here is the cost function derivative after the direction that we choose as a trial direction A. Now we see, okay, this is not a projection yet because the direction is kind of wrapped in the commutator. So we can use cyclicity. The commutator is linear, so cyclicity goes through as it was. So I can shift this H outside to bundle it with the state psi. And then A is left hanging here, which is the equivalent of my probing direction here. So this is the Riemannian gradient G. Okay, so what we computed is that the directional derivative in the direction of A is given by the projection of the direction onto a single vector. That is just the commutator of the two things that we have in hand, which is very beautiful, and that's the beauty of the unitary group. So this here is our Riemannian gradient. It's an element of the tangent space, so I can exponentiate it. I will get a new updated state psi prime. And this thing here will be a well-defined state. It comes after mapping by a unitary, and it will have a decreased energy. Okay. Now I can iterate it. I got a new working point psi. I just need to input this into the bracket with the Hamiltonian H. I can apply that unitary, and I can get a new state. It will again have a decreased energy if S is small enough. By linearization, we get that. Double bracket quantum algorithms are a systematic framework for implementing exponentials of commutators on quantum computers. And this uncovered new unitary synthesis formulas because we can further decompose it using this kind of four-cycle group commutator, and we can prove new things about how much we decrease the energy, whether it converges, and so on. The difficult step was to go beyond that and decompose it further. I will show it in a moment. Just to highlight it, normally our ideal evolutions are linear differential equations. You can either look at observables or the state. Both of them involve a single commutator. If you take the continuum limit of the Riemannian gradient descent above, you will get an equation where the variable appears twice here. So it's a nonlinear differential equation. It will still have unitary solutions by the token of this tangency that I described, but it's difficult to solve it. And it's a good thing because the quantum computer can try to implement it. And because it's nonlinear, it can encode very difficult computational problems for us. All right, and this double bracket equation was first proposed by Roger Brockett in this context of actually computing something with the equation. People have seen it before, but in the year where I was born, actually Brockett recognized that this differential equation gives you the capacity to sortless diagonalize matrices. That was my entry point, and then solve linear programming problems, which is kind of what we want to generalize for quantum computing. So a very powerful paper, very far-reaching foresight by Brockett. As a curiosity, the second paper here is actually what we are using to this day as a subroutine of unitary synthesis to decompose arbitrary 2-qubit operations into a canonical form and then process it further. Okay, so double bracket quantum algorithms are directly inspired by double bracket flows and allow to perform optimization through hopefully short quantum computations. Okay, let's have a look at that. We are ready to look at the orange box to look at double bracket quantum algorithms. So in the scope of the 4 stages of developing quantum algorithms, I stated that we need to find an optimization solver. So we need to find ways to lower the cost function psi h psi. And so let's look at the two difficult parts here. So what are the design choices and unitary synthesis? How can we do it? Actually, before in previous years, there was a lot of developments, but also it has led to a certain crisis where we don't know whether the quantum algorithms that we will be able to use will be fast enough to do it. So people have looked at direct ways to do both the design choice and unitary synthesis through something called the adiabatic theorem. And that leads to the QAOA approach. So the idea is you slowly change the Hamiltonian. Hopefully you can make those changes actually quite large. And then there should be a quantum phenomenon to stabilize the solution space and reach the solution. The problem here is that it's very heuristic. And I'm only hinting at one paper where, for example, the researchers here state, we look at the recently claimed runtime advantage and we see that it doesn't withstand rigorous benchmarking. So it means like if you probe the problem more, the advantage is actually not so strong. And that's the pros and cons of the heuristics. Heuristics can be awesome, but it leads to hype because then it might lead to statements that actually don't hold up under scrutiny. So all we can do is ask journalist questions what, where, why, and apply critical thinking to it. It's a good thing that there are many developments, but they come with certain difficulties of signal-to-noise ratio. The way I described unitary operations to you was that basically we have the watermelon and we select directions, and then we go a certain distance. So sometimes long, sometimes short, sometimes long, sometimes short. A brute force approach is to say, I will select a given set of directions, and I will only manipulate how long am I going in those directions. Then you could say, I will use a machine learning approach. The more data you give me, the better I should be able to find those durations. The problem is that this will get stuck. We know as a community by now this will get stuck. And just to show, to maybe hint at this, this paper that I'm citing here from 2018 shows this, and the debate around it is actually quite interesting. For example, in the referee report, there's a statement, in essence, the authors have created a field out of nothing, kind of this idea of brute force learning, and then have finally realized why it was a bad idea. Actually, this is a very good paper. It actually explains to us a lot about how we can find circuits, but it also shows that this approach cannot work. The way the double bracket quantum algorithms are coming in is that they are guaranteed to converge. And what we are showing recently is that they can pick up after learning of those brute force methods will have gotten stuck. It will get stuck, but we can use it and it's useful to us. So what we showed in my postdoc time when I got the funding to start a collaboration with Stefano Carazza's group, we looked at the typical phenomenon where a brute force optimization gets stuck. Then we apply one step of the double bracket algorithm and we drop down the cost function by a significant amount. That's kind of the idea of knowing which direction to take thanks to the Riemannian gradient theory. So here, there's actually a synergy of the previous methods and we keep learning, and it's not a bad thing if we discover more insights about the thing that we are studying. Okay, so we need those optimization solvers. Other things can get stuck because maybe they are a bit heuristical. Can we have more systematic ways? Well, for optimization, we can take different strategic choices how we will go about it. We could diagonalize and then pluck out the smallest eigenvalue. The problem is that this spectrum will be exponentially large, so maybe it's overdoing it. Maybe we can just target one single state, make an operation to the input, have some output that will just directly look for the eigenstate of the minimal eigenvalue. The problem is that here we can take a design choice to map the input into the output for a non-unitary operation and then normalize it back to the manifold. This is non-unitary, so it has a question of what kind of unitary synthesis to do for that. It's a nice approach because we can choose many different functions, for example, approximations for polynomials. There are systematic ways of doing that, but this kind of quantum signal processing so far before our work could be done only probabilistically, which was a bit of a drawback of the method. Just to say a bit about those methods, they're actually linking to engineering. So given a Hermitian matrix H, we want to prepare the eigenvector lambda 0 corresponding to the lowest eigenvalue. This will be the global optimizer of the cost function, which is a good thing. And then if we decompose in the bracket notation into the eigenspace, this is nothing else but using the eigenvector notation. Then we can also decompose the state. And if we want to apply a function of the Hamiltonian, this function will act through the eigenvalues in this decomposition. So if we can design a low-pass filter that doesn't suppress the contribution of lambda 0 and suppresses everything else, we can do optimization this way. Okay, so those are some ideas how to do it. And double bracket quantum algorithms have provided unitary synthesis for all of those approaches and even for more applications. In all cases, whenever you ask, how do I actually find a unitary to perform this, we find solutions using exponentials of commutators. So that's been a whole roadmap of results that we were finding. And now, if you know about Riemannian gradients, as I showed you, should be not surprised that those exponentials are appearing. Okay, just to wrap up, let me tell you a little bit more details for the experts, how we are performing imaginary time evolution. So this is defined by applying the exponential of h. Then I is missing, so we need the normalization. And the bridge was a hint that came from David Gossett to say, actually, if we look at a small tau expansion, the equation, the differential equation for how this changes is given by a commutator. And then we can take an exponential, find that it's a low short step expansion. But this is really the bridging equation. Here we are in the design. I'm mapping from psi into something useful. And here I'm explaining how to do it using unitary. So this is solving the unitary synthesis. And it's optimizing the energy. So we understand that the Riemannian gradient, which is precisely what we see here, should appear. Now, what we said, we can do this kind of 4-step cycle to approximate an exponential of the commutator. And then my work was in essence about taking it serious and keep iterating it. So for example, if I have a low time, short duration of the imaginary time evolution, I can make certain approximations of this commutator here, and those are unitaries that we can implement. Okay, so what we will do is we take the approximation and then we say, okay, those all compose into a unitary. I collect it as a UK. Then if I need to split and reflect around the input state, I can do it by undoing the preparation, doing an easy state reflection, and then doing the preparation again. And then we have a recursive way of implementing and composing it together. So you really see that it wasn't for nothing that I was talking about the group law of the unitary group. The cool thing is that we can prove things about it. This paper is now accepted at PRL. We have also other results, and the nice thing is that in the paper we show that this really has a low gate count. Of course, the circuit depth will recursively grow, so that's the disadvantage of the approach. But we can actually see that the method works quite well. We can see numerically and illustrations to rigorous proofs that the energy will be decreasing, so we can expand and see how much energy we decrease. And we do it for quite large systems. And then we can look at, for example, convergence properties to the ground state. This is getting harder as the system size increases, but if we compare, for example, to the basic phase estimation, we see our method is much faster because we don't need to resolve the gap in the same way that phase estimation needs it. So, for example, for the continuum high fidelity gates, we could run around 2000, which means we can run about 2 steps, get a fidelity to the 20 qubit Heisenberg model above 90%, which phase estimation wouldn't be able to do without heuristic shifts. So that's the nice thing that we found for specific examples. Just to recap, double bracket quantum algorithms is this bridge between design choices and unitary synthesis. It's a systematic framework for unitary synthesis. We found many solutions, and we really see that those exponentials of commutators are really a powerful workhorse for this. Just to put it into context, and there have been other approaches for constructing powerful algorithms. Maybe this is best exemplified by this paper titled Grand Unification of Quantum Algorithms, which uses the framework of block encodings. Our approach is different. We are using the framework of geodesics to access this kind of cost function Hamiltonian H. And we also see a certain unification, but we also see geometrically why this is possible. Optimizing the energy is an optimization. We are working with unitaries. We should be thinking about Riemannian gradients. So what we have is that double bracket quantum algorithms are coherently implementing Riemannian gradient steps. So the cut in the background symbolizes quantum superpositions. And previous approaches to implementing Riemannian gradients were actually about learning the classical information that encodes them and then compiling it backwards. So we basically start with quantum, go classical, go back to quantum. We are staying all the way within this basket of coherent operations on the quantum computer. This gave us rigorous unitary synthesis for a line of approaches to optimization. And these days, what I need from the community is to actually give me critical feedback. If you use our methods, when is it not fast enough? Do you get stuck? Do you see something else? We can prove things for the linearized regime, which is not practical. We need to take certain heuristic steps, but you might give us insights for studying something cool where maybe we can prove new things and understand more things about the hardness of the intrinsically difficult challenges we want to take up in quantum computation. Just to also connect to the state of the field, we found that training quantum circuits from data doesn't work well, unlike in classical machine learning applications. Classically, the training is empirically not a problem. And what we found in our work is that that we can use variational learning methods as a really cool warm start for double bracket quantum algorithms, and then we can benefit from the rigorous convergence. All right. So yeah, that brings me to the end. That was quite a long journey in the last 4 years. Feel free to stay in touch, and hopefully I can continue working on it in the future.